Hi everyone, welcome to my channel Physics Infinity. Once again, I bring to you a problem on cavity in a conductor, charge inside the cavity and charge outside. But this time, I am going to take a spherical conductor, a spherical cavity, charge inside a cavity, charge outside a cavity, and we'll try to work out, we'll try to analyze, because there are certain things we'll not be able to work out. But I'll show you how you can analyze this situation and try to work out the intensity and potential at certain points. Certain points you cannot find. We'll see. So let me first explain to you the situation. The situation is there is a metallic solid conductor of radius 3a. Well, there is a cavity inside this. There is a cavity. Look at this blue thing. So there is a cavity. Center of the cavity is C. Center of the sphere is O. And within the cavity, I am placing a charge Q, point charge Q, which lies at a distance of a by 2 from the center of the cavity. Mind you, Q is not at the center of the cavity. One thing. Then there is a charge, point charge 4Q of value 4Q, which lies outside the conductor, and it is lying at B, and the distance OB is 4 times A. Radius of the conductor, spherical conductor, 3A. Fine. The cavity is of radius A. So A, 3A, 4A. Remember the figures. I put it on the board. You can take a screenshot later on. Now, I take 3 points. P1 within the conductor, P2 outside the conductor, and P3 inside the cavity. First of all, let us try to evaluate the intensities at P1, P2 and P3. But before we do that, let us try to understand the charge distribution on the cavity wall, on the surface of the conductor, and also try to get how is the electric field pattern for this particular situation. One by one. Let's talk about the cavity first. Within the cavity, there is a point charge Q, and it is off center the cavity. So, close to the point Q, there will be skewing of charges. The electric field will start from Q, that is from A, because the Q is lying at capital A point, and it will terminate on the cavity wall. Field lines cannot penetrate the conducting material. So they'll start from here. Look at this. I've made an elaborated figure. So the field line will start from A and terminate on the inner walls of the cavity. So on the inner walls of the cavity, there will be minus Q charge, not uniformly spread, non-uniformly spread. So I've shown you that close to Q there will be, the density would be higher, and then the charges are far apart, the density is lower. It is not uniform density, remember that. If suppose Q was lying at the center of the cavity, then okay, then the minus Q will spread evenly, but that is not the situation. That could be another situation. That's a simpler situation. Now, if minus Q has come on the walls of the cavity, then on the surface of the cavity there will be charge plus Q. On the surface of the conductor, not cavity. On the surface of the conductor there will be charge plus Q. Normally plus Q should be evenly spread, but in this situation it will not be evenly spread. Why? Because close to the conductor there is a point charge 4Q. Now 4Q will have its own field, so much so that this plus Q on the surface, plus Q, the total charge on the surface of the conductor will be plus Q. But once again, non-uniformly spread. Non-uniformly spread. So much so that close to 4Q, this part I've even shown negative charge. Why? Because the field lines from 4Q, when they are coming towards the conductor, then of course the electrons can rush. I had explained to you in the earlier problem E7, ES8. In the ES8, I had taken a arbitrary shaped conductor and an arbitrary shaped cavity. This time spherical conductor and a spherical cavity. So there also I had explained, if 4Q was not there, then of course plus Q will be uniformly spread. But 4Q will not allow this to be spread uniformly. So total charge on the surface is Q, but non-uniformly spread. Okay, some part is minus here, plus here, that's a different matter. Non-uniformly spread. So we talked about the charge distribution. So now we are dealing with 4 charges. Point charge Q lying at capital A, point charge 4Q lying at capital B, point capital B. Then the charge on the cavity Q cav, which I call as Q cav, total minus Q, non-uniformly spread. Non-uniformly spread. 3. Fourth one, charge on the surface plus Q, total charge, once again non-uniformly spread. Now let's see one by one the intensities at different points. First, at P1. P1 is a point within the conductor. Electrostatic shielding, electrostatic equilibrium, fine. The net field should be 0. So the vector sum, field is a vector, intensity is a vector. So the vector sum of all these 4 charges, some students have the misconception that every charge will create 0 field. No, that's not true. The vector sum of the field contribution of all these 4 charges that I have talked about will give you net result 0 at P1. Another interesting thing, electrostatic shielding. The 4Q is shielded by the charge on the surface. So the field contribution of 4Q and of QS will give you 0. Similarly, Q inside the cavity and minus Q on the cavity wall, their contribution also 0 because conductor will shield this. Now, if I write E at P1, then due to point charge KQ upon AP1 square, AP1 cap, simple point charge, plus E arrow due to cavity. This whole thing should be 0, and similarly the electric intensity due to the point charge 4Q and due to the charge on the surface, which I am calling it as ES arrow, the sum total of this also will be 0. So overall the field will be 0. Very interesting. Now if I ask you a question, what is the field contribution at P1 due to the charge on the cavity? That is minus Q. Very easy, because the sum total of this and E cavity is 0. So E cavity will be negative of this. So E cavity will be minus a KQ upon AP1 whole square and the unit vector AP1 cap. Similarly, what is the field at P1 or the intensity at P1? Same thing, due to the charge on the surface. So once again, this plus this is 0. So ES arrow will be negative of the contribution from 4Q. So easily I have solved this using the concept of electrostatic shielding. So it is done. Now let's talk about the point. Let's talk about the point P2. Where is P2? P2 is outside the conductor. So once again, superposition of fields due to 4 charges. But inside the charge, inside the cavity Q and the charge on the cavity minus Q is shielded by the conductor. So E arrow is 0 due to Q and Q cavity, electrostatic shielding. So two charges contribution comes out to be 0. Now what about point charge 4Q? That's easy, because if this distance is given, so the contribution of 4Q, field contribution of 4Q at P2 will be K charge 4Q divided by distance square BP2 whole square times the unit vector, that is BP2 cap. Easy. Now the last contribution due to ES arrow. Now here becomes a problem. ES arrow we will not be able to calculate. Why? Because the charge on the surface is uniformly distributed. Non-uniformly distributed, sorry, it is non-uniformly distributed. So if I take elemental, I will not be able to do the integration. So this will always, ES arrow will remain a question mark. So we cannot find the electric intensity at P2 due to the surface charge. So overall field, no, sorry, we cannot calculate. Yes, if QS was evenly spread, then it would have been okay. Why? Because then I would have taken the charge for outside points concentrated at center. But that is not the case. That is not the case. The charge on the surface is non-uniformly spread. So its contribution, field contribution at P2 cannot be evaluated. So gone. So overall, the overall field at P2 will remain a question mark for us. Let's now talk about the P3, a point inside the cavity. So once again, contribution from the 4 charges, contribution from 4Q and the contribution of surface. Sum total will be 0. Why? Electrostatic shielding, conductor will shield it. So 2 charges, sum total, contribution gone. Now come the charge Q, the contribution of Q, that is a point charge, and the point is P3. So the contribution of point charge Q at P3, field contribution, will be K charge divided by distance square, unit vector. I have written that at P3. So KQ upon A by 2, where the distance given is A by 2, from here to here. No, at P3, I am sorry, this is not A by 2, this is wrong. It is KQ upon AP3, AP3 square, and the unit vector AP3 cap, done. Point charge contribution easy to find. Now the contribution from the cavity, charge on the cavity, once again we are stuck. The total charge on the cavity is minus Q, but not uniformly spread. So different elemental charge on the cavity have different distances from the point P3. I'll not be able to do the integration once again. So we cannot find the contribution at P3, the field contribution at P3 due to. Okay, let me now talk about the potential in this situation at different points. And the first point I'm going to take is the potential at C. C is the center of the cavity. Right. We have 4 charges. Q lying at A, minus Q non-uniformly distributed on the cavity wall, 4Q lying at B, point charge 4Q lying at B, and of course the plus Q on the surface of the conductor, which is non-uniformly distributed. The net potential at any point is the scalar sum of all these charges. potential due to all these charges? Let's go one by one. First of all, let us tackle the potential due to outside charges. Now, what are the outside charges? Outside to the conductor, 4Q and Q. 4Q and Q. That is shielded. So, they will produce zero intensity, zero field at every point within the conductor and also within the cavity. When that is the case, then that means that whatever potential they create at any convenient point within the conductor will be same everywhere, and the most convenient point is going to be at O. So let's first of all work out the potential at O due to these outside charges, and that will be the same as that at C. All right. So look at this. For the outside charges, the potential at O is K 4Q upon 4A, point charge, plus KQ upon 3A. Right. Agree, Q is non-uniformly distributed, but every elemental charge on the surface is at same distance, 3A from O. So when I do the integration of all that, I'll get the result KQ by 3A. Okay. Now let's talk about the potential at C due to the inside charges. Charges inside the cavity. Of course, there is a point charge Q A by 2 from C. So KQ upon A by 2. And same argument what I have given for the surface charge. On the cavity, there is a non-distributed total charge minus Q. But every elemental charge is at same distance A from here. So when I do the integration, the eventual result will give me minus KQ by A. So I do all these calculation, very simple. It's a simple scalar addition. I get 7KQ by 3A or 7Q upon 12 pi epsilon naught A. I have broken K as 1 by 4 pi epsilon naught. So we have obtained the potential at C. Now let's talk about the potential at O. First let me talk about the potential at O due to outside charges. This will be same as what we did above. Contribution from the point charge 4Q. K into 4Q upon 4A. The distance of 4Q from O is 4A. Plus the contribution from the surface charge, just like I explained just now, it will be KQ by 3A. Right. Now let's talk about the charges inside the cavity and on the cavity wall. Q is a point charge, so its contribution is KQ upon A. KQ upon A. And the contribution from this, that is minus Q, non-uniformly distributed on this cavity wall. But O is an outside point and the conductor shields Q and minus Q and give the field 0 at all points in the conductor. This means that the movement of Q, now this is a very important point, the movement of Q anywhere within the conductor is not going to disturb the electric field at any point in the conductor. Okay, suppose Q is at C, then in that case Q cavity will be minus Q but uniformly distributed, and in that case the contribution of Q and minus Q on the cavity will become 0 at all points in the conductor outside the cavity. In fact, outside the cavity, in the conductor and even outside. So the contribution of the charge within the cavity and on the cavity wall at O, this whole thing would turn out to be 0. So I am left out only with this. I add, this is 4 by 3 kq by A. I break K. So Q upon 3 pi epsilon naught A. Beautiful. We have at least done the potential at the center of the cavity and at the center of the sphere. Now let's talk at P1. Potential at P1 within the conductor. As far as the outside charges are concerned, Vp1 is VO. Vp1, V at P1 is same as V at O due to outside charges, constant, and due to the cavity wall and the charge within the cavity, the contribution is 0. I've just explained. So V at P1 is same at V at O due to outside charges. So that is done. Now let us talk about P2, a point outside the conductor. Due to Q inside the cavity and on the cavity wall, I have already told you, outside field is 0, the contribution as well as potential is 0. So due to Q inside the cavity and minus Q on the cavity wall, the contribution is 0. Done. Now let's talk about the outside charges. The potential at P2 due to 4Q. Now this is a point charge. It will be K into 4Q divided by BP2. BP2, the distance. Positive contribution, 4Q is positive. Keep it. But the contribution from the plus Q on the surface will remain unknown. Same reason that it is non-uniformly distributed. How will I do the integration? Cannot do. Elemental charge, every elemental charge will have different charge density, so it cannot be done. So overall potential at P2, I put a question mark, cannot be found, we cannot do it. Now let's talk about the point P3 within the cavity. Now V3 in the cavity, once again, outside charges, the potential at P3 is same as the potential at C, which we have done. Whatever contribution is the potential due to 4Q and the charge on the surface at O, at P1, at C, anywhere in the cavity will remain same, so that can be found, no problem. But once again, the cavity will create a problem. At P3, the potential due to Q, okay, that can be known, KQ upon A P3, the distance. But the contribution from the cavity wall, non-uniform distribution of the charge, non-uniform surface charge density, we can't do the integration, we cannot find. So I put Vp3 also as a question, basically because one particular charge, that is a charge on the cavity, is creating problem. We cannot find its value, so overall we cannot. Individual, suppose we have a problem where individual charges, contribution from individual charges, then at least from the 3 charges we can find, but the contribution from the charge on the cavity wall we cannot find. So overall we will not be able to get the exact value of the potential at P3. Now this was one video that I prepared for you, which can give you a total insight into this very advanced understanding of induced charges and the intensity and induced charges, charges in the cavity, within a conductor, outside the conductor. I think this should really enhance the skills of some very good students, especially the JEE Advanced. I hope you have enjoyed. I would request you to see this video in the landscape mode so that you can see each and every step clearly and understand every point that I have spoken to you. For any comments, please don't hesitate. If you have any doubt, write it in the comment. I'll be too glad.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.